Hi there, and welcome to our project, Twemoji. In this project, we use machine learning to predict emojis based on tweets. I'll first be introducing our dataset, and then we'll discuss pre-processing, word embeddings, the models built, their evaluation, as well as our final reflections. Let us first discuss our problem statement, which will be divided into three. Firstly, how can we recommend emojis for tweets so that users don't have to spend time to find it themselves? Secondly, how can we ensure that we predict the most appropriate emoji depending on the context? And thirdly, if Twitter got a new reaction feature, how could we recommend emojis in response to tweets? Well, let us try and understand the Twemoji Dataset. This was published by Amsterdam University in 2018 and contains over 13 million tweets. However, this dataset is imbalanced and the number of tweets for each emoji varies significantly. The dataset consists of the files shown here. These files were the main dataset, which consisted of the tweet ID and the emoji annotations, and was split into train, test, and validation. This one is a subset, which included a third column for image URLs. Then we have a balanced version of the test set, and lastly, a mapping of the emoji IDs with their metadata. Some points to note about the main dataset are that some tweets are tagged with multiple emojis, as seen by more than one ID under annotations. And some tweets are quoted reply tweets, and they can be identified with the _Q after the tweet ID. Now, before we retrieve this dataset, we cleaned it by removing tweets that have multiple distinct emojis, since a string of emojis could be used to tell an entire story and can get complex. Secondly, we removed the quoted tweets, as they're more like comments rather than original tweets and hence need context. Lastly, we dropped those emojis that weren't used in all three train, test, and validation sets.
Hello, my name is Andrew, and today I'm going to discuss how we pre-processed and retrieved our dataset. The provided dataset includes tweets that use a wide variety of emojis. We initially chose the 20 most popular emojis after cleaning. However, due to the similarity between some emojis and the scale of the project, we later decided to focus on only 5 emojis before training the model. They are the red heart, face with tears of joy, grinning face with sweat, smiling face with heart eyes, and face with rolling eyes. Using Twitter developer accounts, we downloaded 80,000 tweets for training and 10,000 tweets each for validation and testing. Only a small portion of the tweets could be downloaded, however, as about 2/3 of them were no longer available. The primary reason for this is that the original account was made private or even terminated. To balance the dataset, we supplemented the ones with a lot of missing data from a similar emoji dataset called emotag. To standardize our models, we used the same train validation test split across all of them. The distribution of emojis is fairly even, with only 6% more of the most popular emoji than the least popular emoji in the dataset. In terms of text preprocessing, we started by tokenizing the tweets with the tweet tokenizer and removing the stop words with the NLTK corpus. Next, we converted all the words to lowercase, removed all the tokens that are non-alphanumeric, and lemmatized each word. Finally, we deleted all the characters with non-English ASCII values.
For this project, we are doing text classification that requires features to be learned from the words, and word embeddings can help with that. And then later we can map it to an emoji here. The idea behind is that the embeddings represent each word as a real valued vector, and similar words will have similar representation. So by this, the models can learn the meaningful relationships between words. When experimenting with what kind of embeddings to use, we had 4 different types of them explored. The most simple types are the bag of words and n-grams that were taught in the lecture. However, bag of words does not consider order or grammatical structure of a word, and n-grams does not strongly capture the context of words. So they were not the most appropriate for the sparse tweet data that we had. So we ended up choosing TF-IDF and GloVe to compare our models again, since the embeddings are different in terms of how they make sense of words. We can examine whether context means a lot for the emoji to be predicted right, or if the model can make do with the understanding of the significance of a particular word. GloVe has also been used and referenced in many of the emoji prediction work done previously and has produced good results. So let me elaborate on the embeddings. TF-IDF computes the frequency of a word in a sentence and also in relation to the entire document. So the measure is as specified here in this formula. So common words have a lower score while the unique words have a higher score, which means they are more relevant to the document. Through this, we can detect how important a word is to a document in a corpus and can be used to predict emojis with respect to the entire tweet. One disadvantage of TF-IDF is that it can produce a sparse matrix. So due to the curse of dimensionality, having too many input variables tend to lead to overfitting and slower model training. So we used truncated SVD, which is a kind of dimension reduction technique that factorizes a sparse matrix by TF-IDF. So for the TF-IDF embedding in our project, we used a hyperparameter K value of 300. To elaborate on the GloVe embeddings, it's similar to Word2Vec in the fact that each word is represented as a vector, but GloVe takes a global context, which is, in our case, is the entire tweet list. GloVe computes the probabilities with which a word might co-occur with another throughout the entire tweet list and projects it onto a co-occurrence matrix like this. Through this, it helps in solving our problem statement of a context-specific prediction of emoji. So for our project, we use the pre-trained models released by Stanford. Among the 4 pre-trained models, we use the one trained on the Twitter corpus that contains 21 billion tokens of 100 dimension. So now that the embedding layer has been elaborated, I'll pass over my time to Benedict, who will describe the different machine learning models that we experimented with.
Now, we'll bring you through the models that we've considered to tackle for our classification problem. There are 3 general types of models and approaches that we've considered. First are the linear models, which act as our baseline models. Next are the neural networks that we train to model non-linear dependencies of our text data. Last but not least, we also tried using transfer learning using some of the state-of-the-art models. Let's start with our baseline linear models. We considered 3 models that we learned from our lectures: support vector machine, logistic regression, and random forest, which is an ensemble of decision trees. I'll now bring you through some of the key considerations for model building for each of these models. Our first model, SVM, in its base form, isn't suitable to be used directly for a multi-class classification problem, as it can only linearly separate between 2 classes. To support multi-class classification, we use the C support vector classification from the sklearn library, which can handle multi-class problems via 1 versus 1 scheme. How a 1 versus 1 model works is by generating a binary classifier model for each pair of classes, which results in n times n minus 1 divided by 2 number of models. This allows us to create boundaries between each pair of classes and ultimately lets us separate our different classes. Some other considerations when we built our model was due to the time complexity of generating these pairwise models, we could only trial the default kernel type, which was RBF, and to simplify the representation of the glyph embeddings of a sentence for linear models, we had to use np.min to get a single value per sentence. This meant that our linear models resulted in us ignoring the 3D representation of a sentence. For logistic regression, we also used the multinomial version from sklearn, which generalizes the model to multi-class problems. Since this is a cheaper model to train, we did some hyperparameter tuning using the different solvers and regularization values, and found that the best combination was the Newton CG solver with C equals to 1 and L2 penalty. Likewise, np.min was used to simplify our glyph embeddings. Random forest is also one of the models that we experimented on, and for our decision tree variants, tested out a few variant models from the sklearn library, such as the base model, random forest, gradient boosting, adaptive boosting, and extra trees. We found that random forest had the best results, probably because of noisy data and the objective of multi-class classification. We settled on random forest for our project, and it's essentially an ensemble learning method that constructs a multitude of decision trees at training time. And by having an ensemble, we reduce the variance of each individual model, which reduces overfitting on noisy data in our dataset. We also did hyperparameter tuning with the random forest models based on a criterion, max features, max depth, and an estimator. Due to the complex nature of text data, linear models may not work very well in modeling some of the non-linearities in the data. Thus, we considered some neural networks which can model these non-linear dependencies better, such as the simple NN, CNN, and a variant of the RNN, the bi-LSTM. Our simple neural network, which acts as another baseline for our other NN models, consists of 3 alternating layers of dense neurons and dropout layers. We considered using CNN as well, due to its capabilities of capturing the general context of a whole sentence due to the use of convolution layers. For CNN model, we kept it simple and utilized 2 of such convolution layers with a max pool layer in between. Finally, we also considered capturing the sequential relationship of a sentence using bi-LSTM, which is a variant of the RNN. From multiple research papers that we've read, we found that bi-LSTM gives good performance on similar classification problems such as sentiment analysis and counters the vanishing gradient problem that traditional RNNs face using the bidirectional LSTM layers, which allows for information flow to travel both forward and backward in those layers. This means that we are able to have the input flow in both directions and utilize information from both sides. For example, we are now able to get contextual information from each word, from the words before it and after it.
Next up, I'll be talking about transfer learning models. Transfer learning models require lesser training data and is faster than training a machine learning model from scratch, since the models leverage knowledge from previously trained models, hence we consider the transfer learning models. Firstly, our initial considerations for the transfer learning models were BERT-TWEET, DistillBERT, RoBERTa, and BERT-based. However, our final transfer learning models used were BERT-TWEET and DistillBERT. BERT was taking too long to train due to the large amounts of data required, hence DistillBERT was better since it's a smaller version of BERT. Given that BERT-TWEET was pre-trained on English tweets, it was determined to be a better model for our problem since our dataset was based on tweets compared to RoBERTa, which was based off a general English data. First, we have the DistillBERT, which focuses on the distillation method to compress the BERT-based model into a smaller, cheaper model with 60% of parameters as compared to the original model. Distillation is a process of training a small student model to mimic a larger teacher model as close as possible. Next, we have the BERT-TWEET, which is a language model pre-trained on English tweets. The flowchart depicts the process by which the tweets were collected and how the model was trained. Next, we move to the model evaluation. We used confusion matrix as well as classification report as our model evaluation metrics. Since we have 2 word embeddings, we compared the confusion matrix and the classification report across both word embeddings. First up, we have the confusion matrix for the TF-IDF. the glove confusion matrix, as well as the transfer learning confusion matrix, which is based off the word embedding. Since our data set is relatively well balanced, we use macro average as we want to check the overall accuracy of each class. In general, we observe that the linear models do not perform as well as the complex models. This may be due to the linear separability issue, so tweets cannot be interpreted using linear models and need more complex models. For linear models, we observe that TF-IDF perform better than GLOVE, whereas for neural network models, GLOVE perform better than TF-IDF. The difference in performance between the two word embeddings for various models can be because TF-IDF only considers the importance of a word to a particular tweet and does not consider the co-occurrence or the context in which the words appear. GLOVE takes into consideration and is made for complex models such as LSTM or RNN, and that could be why it produced better results compared to TF-IDF, especially for a tweet dataset. The tweets contain a lot of words with semantic differences, and with GLOVE, the neural network can better learn the complex relations between them rather than just using term frequency. Upon comparing the various models, we have discovered that the transfer learning model per tweet performed the best. This may be due to the large prior knowledge from pre-training models which the models trained from scratch do not have. However, that being said, here are some limitations due to which our transfer learning models may not have achieved optimal accuracy. Transfer learning models have some limitations which include negative transfer as well as overfitting. Transfer learning only works if the initial target problems are similar enough, and there are no specific standards on which tasks are related or how algorithms decide which tasks are related, which makes it challenging to find solutions to negative transfer. Also, in transfer learning, we cannot remove the neural layers to find the optimal AI models with confidence, hence overfitting can easily occur. The process to decide how many layers and neurons to remove so that the model does not become overfitting is time-consuming and challenging, hence making it difficult to find solutions to overfitting. Thank you.
Finally, I'll take you through our group's reflection for the project. To start off with our issues phase, our dataset was generally small due to previously deleted or private tweets. As such, we only used about less than 1% of the entire dataset. We had to forgo tweets with multiple emojis to limit the complexity of model training. This hindered training of more complex transfer learning and our deeper neural network models since we were unable to increase hidden layers in CNN or BioSTM to prevent overfitting, and we could not capture greater nonlinearities in tweets. Secondly, there were longer training times for SVM and transfer learning. It was time-consuming to hyperparameter tune the SVM, especially because the training time of ON³ was considerably long. Slangs and misspelled words also affected the GLOVE embeddings, creating a different word representation and limited the performance of our models. Moving on to our learning points, when we analyzed the performance of our linear models, we observed that TF-IDF performed significantly better than GLOVE embeddings on the test set. Primarily, we found that MP.mean to aggregate word embedding score across a sentence eliminated crucial information of the tweet in predicting its corresponding emojis. This explains why BioSTM performed significantly better than linear models on GLOVE embeddings on the test set. We also found that truncated SVD was useful in dimensionally reducing sparse matrix for TF-IDF, which reduced overfitting. To further understand our limitations of our GLOVE embeddings, our group looked at the cosine similarities of words in similar tweets. For the tweet with a ground truth of the double heart eye emoji, we saw that the word representation vector for the slang cutie and cutes had a rather small cosine similarity, even though the underlying meaning was the same. This meant that the angle between the vector representation of the both slangs were large. Across a sentence, when comparing the tweets OMG he's a cutie and damn so adorable, our group also found relatively small cosine similarity. This is a problem affecting tweets as slangs are extremely prevalent due to conversational tones used in tweet construction. Slangs also carry deeper nuance, and our team faced a challenge in correcting slangs to its base word, as it could change the entire meaning of a tweet. Given our issues faced and the learning points drawn from the project, further work can also build on what we have done. Firstly, there's room to expand beyond 5 emojis and predict more emojis up to 20. In addition, multi-label predictions can be included since tweets contain a mixture of emojis in the real world. Lastly, there exists an opportunity to fine-tune embeddings through training our own word-to-vec using CBOW or skipgram for tweets containing tags, hashtags, and emojis across a larger corpus of tweets to address these issues than the GLOVE embeddings that we use. So how does our project provide additional value? Currently, existing research focuses on the performance metrics for emoji prediction, with much research focusing on the effectiveness of BioSTM or CNN with GLOVE embeddings on tweets. Our project value adds to existing depth of literature by evaluating different word embeddings on each model, from linear models to deep neural networks, highlighting why certain embeddings work better / worse on each model respectively. We hope that by doing so, we can understand the nuance of each tweet better and find an effective word representation for model training. Our group would like to give credit to these resources which have inspired and helped us in our research. Thank you so much for your time, and we hope that you have learned something.